So with section 8.6, we're going to look at the irrational number e and change of base. So irrational number e actually kind of throws people, and yet remember, it's just a number. So that e is a symbol that represents a number, a decimal. Specifically, it represents 2.71828, blah, blah, blah. Keeps going. It's irrational, meaning it won't stop, it won't repeat. It is very similar to pi. People are very comfortable with pi because we've used it a lot. Same thing with irrational number e. That e simply represents this number. Okay? So if we are looking to graph the function, okay, where the irrational number e is the base, and this is an exponential function, okay? So let's just think about this a minute. So this e here really represents 2.718, and then it would keep going, okay? So that is a base that is greater than 1, and we know that bases that are greater than 1 are increasing, okay? So that means as we go from left to right, they're going to increase, and we refer to these as growth curves. They're exponential growth curves. So we're just going to, if we were to create a t-table and put whatever numbers we want for x, so let's just pick 2, 1, 0, -1, -2, okay? And you put those into your calculator, okay? So I'm going to, there is a place on your calculator where you've got the natural number e. And my calculator has disappeared. So we're just going to keep moving here. There are some of these calculator values right here. So anyways, you put it in your calculator and you put e squared, and that is going to give you, as you see here, I'm just going to round this, 7.389. That's not a comma, it's a decimal. Then you put in e to the first, okay, that's going to be 2.718. E to the 0 is just going to be 1, because anything raised to the 0 power is 1. Then you put e to the -1. Well, we've got that answer right there. So that's going to be 0.367, but I'm going to round that up to 8. You look right there, there's your decision maker. And then you put e to the -2, and that's going to give you 0.135. So then we go ahead and graph those guys. So as we graph them, we've got 2, and then we just estimate 7.3, I don't know, right around there. Then we've got 1, and then we estimate 2.7. Then we've got 0, 1 right there. It's on our y-axis. And then we've got -1.38. And then -2, a little bit closer to 0. And so you can see that we have this very expected growth curve. That is the function of irrational number e. Okay. So now let's look at our natural logarithm. So a natural logarithm is a base e. Okay. So we write our natural log as y is equal to natural log x. What does that mean? Well, we've got y equals natural log x, but if that kind of throws you, and for a lot of people it does, you can substitute for this natural log. You can just put in log base e. It's exactly the same thing. So a natural log is a log. All right? It is. And so if we graph our natural log that has a base e, okay, let's go ahead and just put some numbers here in here for x. And so that's going to be, we're going to put in a 0, 1/2, a 1, a 2, a 3, okay? Well, when we put in a 0 for our x, we get an error. Because remember that logs get really close to 0, but they don't equal 0. Your argument can never equal 0. All right, so there is no value there. Just like your argument cannot be a negative. That's when I picked my x's, I didn't pick any negatives. Otherwise, I would have gotten an error for those. When I put 1/2 in for my natural log, so if I do natural log of 1/2, that's going to give me negative 0.693. Keeps going, but I just rounded. Okay. Then if I go ahead and put in a 1, so that'd be natural log of 1, that's going to give me a 0. If I put in natural log of 2, we can see it's right here. Okay. Oh, there's 1/2. And so that's going to give us 1.098. And then if we put in natural log, oops, I'm sorry. This one would be 0.693. And then we get 1.098, okay, which when I round it really should be 0.99. Okay, so now let's go ahead and graph that. So 1/2 and then negative 0.6, I don't know, right there. Then I've got 1, 0 right on the x-axis. Then I've got 2 and 0.693, and then 3 and a little bit over 1, okay? And so it looks like it's in a straight line. It's not. It would be something like that, okay? There we go. So the natural log and the log of the exponential function e to the x are inverse functions. Okay. Now, all the properties that we learned in the last section, they all apply to this because a natural log is a log. So everything you've learned applies here. All right, so let's go ahead and look at some of these. Now, this first one for 3, that's just e raised to the second power. So that is the same, oops, the same as 2.718 raised to the second power, which is simply going to be 7.389. There's no log, no natural log. It's just a base. It's just a regular exponent, a base being raised to the power of 2. Now, in this next one, this is an exponent, but it's being raised to the natural log of x. Okay, so all of our properties that we had before work here. So I could rewrite that as e raised to the log base ex. So anytime I have the base of my exponent and the base of my log that match, then that is going to be equal to that argument. All right, so let's go ahead and look at 5. So again, if you're having a hard time seeing this one, you could take and you could substitute for that natural log, you could substitute log base e. So then our argument is e to the 5 minus 3x. So again, I have my two bases which match. the base of my log and the base of my exponent, and so it's going to be equal to 5 minus 3x. So what is this last one? 6. It would simply be 2x plus 3. I know. You just need to kind of get comfortable with these and practice. It really is helpful if you don't see it, if it's not intuitive to you. It is helpful to substitute log base e every time you see natural log. You can go back and forth. It's totally fine. All right, now let's apply some of those properties for expansion just like we were doing before, but these are going to be natural logs. So this is going to be the natural log of 3x minus the natural log of e squared. So I'm going to take this first one, this first term. I see that I have 2 factors in my argument, so that's going to cause me to create 2 natural logs that are added. So it'll be natural log of 3 plus natural log x minus. I'm going to take this 2, and I can use my power and put it in front. So it'll be 2 natural log e. Now, can I simplify any of this? Absolutely. The natural log of e is equal to 1. So this natural log of e would be the same as 2 times 1, which is just 2. So my final expansion will be natural log of 3 plus natural log x minus 2. Let's look at the next one. Okay, let's use a different color. So this is going to be natural log x squared y minus natural log square root z. I'm going to separate these first two, this first term, into 2 natural logs that are added. So natural log x squared plus natural log y minus, I'm going to take and convert that radical to a fractional exponent. So natural log of z to the 1/2. So now I can take both of these powers and bring them out front. So that's going to leave me with 2 natural log x plus natural log y minus 1/2 natural log z. That one's done. See, they're not so bad. Exactly how you did them before. Okay, just like we were able to take something that's already been expanded and bring it into a single log, it works just the same. So, a couple things that we look for. We look for the subtraction signs. That means that both of those arguments are going to become factors that are multiplied in the denominator. Okay? Anything that is a coefficient is going to become a power to each of those arguments. So this is going to give me, I'm going to write my natural log, then my argument is going to be a fraction. On the top, it's going to be 17 to the 1/4. In the denominator, I'm going to have y squared times x. The only thing I'm not crazy about is that 17 to the 1/4. So I'm going to make this natural log of the 4th root of 17 over y squared x. Now I'm good. Okay. All right. So let's do this next one. So this one only has, it does have a subtraction sign, but only one. So there's only going to be one factor in the denominator. So this one, I'm going to take natural log, put my fraction bar. And so in the numerator, it'll be x cubed y to the 9th. In the denominator, it would be z to the 1/2. Well, z to the 1/2 is the square root of z. So I'm going to rewrite this as natural log x cubed y to the 9th square root of z. There we go. You got it. Now, all of those examples have had where I've had a fraction. Not every time when we expand do we get a fraction. So let's do this one just for fun. I'm just going to do it off the top of my head. I kind of love this one as an example. Okay, so if you take the natural log of m, actually, natural log of I, okay, plus natural log of a heart, okay, plus natural log m plus natural log a plus natural log t plus natural log h. Of course, you got natural log I love math. Okay, no fraction because there's no subtraction signs. All right, let's look at the change of base formula. So one of the things about, recall about the log function that's on your calculator is that is just base 10. Just like the natural log function on your calculator is log base e. So not every log is a base 10, nor is every log obviously a natural log. So how do we deal with logs that are not a base 10? Well, we set up a ratio, okay? And that's called change of base. So literally all you do, if you've got right here, this log, okay, log base b of x, then in my mind, I just kind of draw this little dotted line. You don't have to really draw it. So the x, okay, becomes your argument for your log in the numerator, and your denominator will be that b. So why do we have an a here? Because that's kind of confusing. Well, you could write this as a ratio of just log x over log b, and those would be both base 10. Or you honestly could write it as a natural log, like log base e of x over log base e of b. But we don't write log base e. That is exactly the same thing as natural log x over natural log b. So what am I trying to say? I'm trying to say that when you're using the change of base formula, okay, all you're doing is setting up a ratio of logs. And so it doesn't matter if you use a common log or if you use a natural log. The thing is, those are the two you'd want to use because that's what's on your calculator. And you can use either one and you get exactly the same answer. Wow, that's pretty cool. Okay, so let's go ahead. There's that example right there where log base 3 of 50, but I'm going to go ahead and just kind of jump in with this one, log base 5 of 27. So you could set this up as using logs as log of 27 over log 5, okay? And when you put that in your calculator, you get approximately 2.048, okay? So then do it with natural log, okay? So you'd set it up as natural log of 27 over natural log of 5. Intuitively, it doesn't seem like it should equal the same thing. And yet it does, because they're just setting up two logs with the same base, and you still get 2.048. If you want to check your answer, remember what a log is. So a log is that exponent. That's what a log is. So I can check this by taking the base of that log, 5, raising it to our exponent, 2.048, and it should give me approximately 27. Really, really close. Okay? All right. So then for 11, you could just try this one on your own. All right? So it'd be log 0.251 over log 7. That would give you approximately negative 0.710. All right, we're going to look at a common application of this irrational number E, okay, which is doing continuous compound interest. All right, first, let's look at some examples where you've got a finite number of compound periods. And that's what this first formula is, okay? It's when we know exactly how many compound periods we have. Well, okay. And here's what all of your variables stand for. All right. So it says N, which is the number of compound periods. And here we've got N. You need a little bit more information for that. So when you're talking about compound periods, they're not going to tell you exactly, oh, here's the number of compound periods. They're not going to give you a number. They're going to give you a word that you have to figure out what the N is. It's not hard. So if they say the interest is compounded annually, that means N is 1. That means interest is compounded just once per year. If they say it's semi-annually, then that means interest is compounded twice a year. So N is 2. Quarterly, N is 4. Monthly, N is 12. And then daily, which that happens, N is 365. All right. So when your interest is compounded continuously, all right, so that is when you're going to use this second formula. And it'll have that word. It'll say compound is, your interest is compounded continuously. And that's your clue that you need to use this second formula. Okay, so how does this work? Let's just go ahead and do an example here. So for this one, your principal, and I find it best to just write out the numbers we're going to use. So the principal is your initial amount that's invested. So that's $12,000, okay? Then your interest rate, your R, your small r, is 7%, but that is always converted to a decimal, so 0.07. Then your N, in this case, your number of compound periods, it says it's quarterly. So that means N is 4. And then your time is in years. So it'd be 9 years. So then I just go ahead and plug everything into the formula, okay? So that's going to be, I'm looking for the amount of my investment after 9 years. So when my T is 9, okay? And so that is going to be, my formula is P times 1 plus R over N raised to the N times T. So then I just plug all my numbers in. So that would be 12,000 times 1 plus, and that 1, by the way, is part of the formula. It doesn't change. So then that's going to be 0.07 over 4 raised to the 4 times 9. Now let me give you a clue. As you put this into your calculator, do not round. You don't round until until you're done with all your calculations. You don't round till then, and then you round to the nearest penny or the hundredths place. So this is going to be approximately, when I put it in, $22,408.89. Okay, so the next one is exactly the same. Okay, same type of deal. I am just going to go ahead and tell you how you set it up. It'd be A of 5 equals 480, 1 plus 0.16 over 12 raised to the 12 times 5. When you put that in your calculator, you get approximately 1,062.63. Okay? All right. Now, this next one is one where it's compounded continuously. So we use sometimes it's referred to as our PERT formula. Okay, so this one, it's going to be A of t is equal to our principal. Then it's going to be our irrational number E raised to the interest rate times time. Okay, so for this example, I would set it up A of 6, because we have 6 years. And then I've got $10,000 invested. I've got my E, irrational number E, raised to the 0.05 times 6. Put that into your calculator. You would get approximately 13,498.59. Here we go. All right. Well, have fun with these.